Earth's days are mysteriously getting longer, scientists say. Matt King, director of the ARC Australian Centre for Excellence in Antarctic Science, University of Tasmania, and Christopher Watson, senior lecturer, School of Geography, Planning, and Spatial Sciences, University of Tasmania. Atomic clocks, combined with precise astronomical measurements, have revealed that the length of a day is suddenly getting longer, and scientists don't know why. This has critical impacts not just on our timekeeping, but also things like GPS and other technologies that govern our modern life. Over the past few decades, Earth's rotation around its axis, which determines how long a day is, has been speeding up. This trend has been making our days shorter. In fact, in June 2022 we set a record for the shortest day over the past half a century or so. But despite this record, since 2020 that steady speedup has curiously switched to a slowdown. Days are getting longer again, and the reason is so far a mystery. While the clocks in our phones indicate there are exactly 24 hours in a day, the actual time it takes for Earth to complete a single rotation varies ever so slightly. These changes occur over periods of millions of years to almost instantly. Even earthquakes and storm events can play a role. It turns out a day is very rarely exactly the magic number of 86,400 seconds. The ever-changing planet. Over millions of years, Earth's rotation has been slowing down due to friction effects associated with the tides driven by the Moon. That process adds about 2.3 milliseconds to the length of each day every century. A few billion years ago an Earth day was only about 19 hours. For the past 20,000 years, another process has been working in the opposite direction, speeding up Earth's rotation. When the last ice age ended, melting polar ice sheets reduced surface pressure, and Earth's mantle started steadily moving toward the poles. Just as a ballet dancer spins faster as they bring their arms toward their body, the axis around which they spin, so our planet's spin rate increases when this massive mantle moves closer to Earth's axis. And this process shortens each day by about 0.6 milliseconds each century. Over decades and longer, the connection between Earth's interior and surface comes into play too. Major earthquakes can change the length of day, although normally by small amounts. For example, the Great Tōhoku Earthquake of 2011 in Japan, with a magnitude of 8.9, is believed to have sped up Earth's rotation by a relatively tiny 1.8 microseconds. Apart from these large-scale changes, over shorter periods weather and climate also have important impacts on Earth's rotation, causing variations in both directions. The fortnightly and monthly tidal cycles move mass around the planet, causing changes in the length of day by up to a millisecond in either direction. We can see tidal variations in length of day records over periods as long as 18.6 years. The movement of our atmosphere has a particularly strong effect, and ocean currents also play a role. Seasonal snow cover and rainfall, or groundwater extraction, alter things further. Why is Earth suddenly slowing down? Since the 1960s, when operators of radio telescopes around the planet started to devise techniques to simultaneously observe cosmic objects like quasars, we have had very precise estimates of Earth's rate of rotation.
To most people, there are exactly 24 hours in a day, the ground only moves during an earthquake, and the Earth rotates just like it does on a globe. And generally speaking, that makes sense. But scientists who like to find out exactly what's going on know the ground actually moves around quite a bit. Days are never quite 24 hours, and the Earth actually wobbles on its axis in a very particular way as it revolves around the Sun. Scientists know all this by using a technique called very long baseline interferometry, which is basically a fancy term for using radio dishes to very precisely measure the Earth's orientation. VLBI was originally developed back in the 60s to take pictures of quasars. Early on, though, someone realized that because quasars never really move, you could use them as reference points, throw the whole process in reverse, and figure out how all the telescopes were moving relative to one another. Basically, when a quasar emits a radio wave, that wave reaches different telescopes at different times. For astronomy, you'd use a computer to imitate a giant telescope and get a good picture of the quasar. But if you instead pay close attention to the time differences, you can use geometry to figure out how far apart the telescopes are. And by making lots of those measurements, you can start to see how the ground beneath the telescopes moves around, when you have to adjust your clock, and that the Earth wobbles on its axis as it moseys around the sun. So the next time you feel like you've had a long day, or that your house is a few millimeters from where you last left it, you can switch on a bunch of radio telescopes, point them at quasars, and find out just how right you are.
A comparison between these estimates and an atomic clock has revealed a seemingly ever-shortening length of day over the past few years. But there's a surprising reveal once we take away the rotation speed fluctuations we know happen due to the tides and seasonal effects. Despite Earth reaching its shortest day on the 29th of June 2022, the long-term trajectory seems to have shifted from shortening to lengthening since 2020. This change is unprecedented over the past 50 years. The reason for this change is not clear. It could be due to changes in weather systems, with back-to-back La Niña events, although these have occurred before. It could be increased melting of the ice sheets, although those have not deviated hugely from their steady rate of melt in recent years. Could it be related to the huge volcano explosion in Tonga injecting huge amounts of water into the atmosphere? Probably not, given that occurred in January 2022. Scientists have speculated this recent, mysterious change in the planet's rotational speed is related to a phenomenon called the Chandler wobble, a small deviation in Earth's rotation axis with a period of about 430 days. Observations from radio telescopes also show that the wobble has diminished in recent years. The two may be linked. One final possibility, which we think is plausible, is that nothing specific has changed inside or around Earth. It could just be long-term tidal effects working in parallel with other periodic processes to produce a temporary change in Earth's rotation rate. Do we need a negative leap second? Precisely understanding Earth's rotation rate is crucial for a host of applications. Navigation systems such as GPS wouldn't work without it. Also, every few years timekeepers insert leap seconds into our official timescales to make sure they don't drift out of sync with our planet. If Earth were to shift to even longer days, we may need to incorporate a negative leap second. This would be unprecedented, and may break the Internet. The need for negative leap seconds is regarded as unlikely right now. For now, we can welcome the news that, at least for a while, we all have a few extra milliseconds each day. Matt King, director of the ARC Australian Centre for Excellence in Antarctic Science, University of Tasmania, and Christopher Watson, senior lecturer, School of Geography, Planning, and Spatial Sciences, University of Tasmania. This article is republished from the conversation under a Creative Commons license.